let's then install the software that we have to install. So take out your phone. I'm assuming everybody has a smartphone. This is like the 21st century. Go to the App Store, and you can install Phyphox. P-H-Y-P-H-O-X. So I'll write it up on the board. P-H-Y-P-H-O-X. This is basically just an app that sets your background to a picture of me, and it costs like 20 bucks, and that goes right into my bank account, so it's a pretty good deal for me. Okay, not really. It's an app that's created by some physics professors that allows you to use the instruments in your phone, like the accelerometer that is used to determine whether your phone's oriented upright or sideways, and put those to good use in physics labs. So you can measure magnetism, you can measure, like I said, acceleration. There's timing things in there. It's an interesting little app, and we'll use it in some of the online labs. So you'll actually be able to take data yourself from home, which is kind of cool. So, all right. And so once you have Phyphox installed, everybody finding this okay? Yeah? Okay. So once you have that installed, I want you guys to open up Excel. Open up Excel and open up whatever workbook you're going to use for today. Save the file to whatever folder you're going to use for this class. Call it like Freefall Lab or something. How many of you have like some experience with Excel? Like you kind of know how to do some things. Okay, a few of you. Okay, it doesn't look like I get too many people feeling confident in Excel, so I'll just assume that we're starting from pretty much no knowledge. So I'll walk you guys through how to make the first couple columns for today, and you'll learn a few of the different operations then. But the first thing that we have to do is enable this data analysis tool pack thing. So if you go to Excel under the File menu. So on Excel, click on File on the upper left-hand corner there. Down at the lower left, you'll see Options. So click on Options. Then a little dialog box pops up. Click on Add-ins on the left-hand side. Okay. So everybody got to the add-ins thing? Yeah? Good? Okay, cool. So down at the bottom there, there's a button that says Go. Go, ... Click on Go. Okay. And you'll see there's like 4 things there. The top 2 to say Analysis Toolpack and Analysis Toolpack VBA. Click on both of those and then click OK. Okay, now, any problems? Do you have a problem? No? You got it? Yeah, I got it. Okay, everybody's got them enabled? Okay, good. Okay, cool. So it doesn't really like give you any feedback or anything, but if you click on the data menu now and go all the way over on the right-hand side, you might have to maximize the window, but there should be a button there that says Data Analysis. Okay, does everybody see the Data Analysis button? Yeah? Okay, good. That data analysis button is that's what we just enabled there, and that'll be useful for you later on in this lab. Okay, so then let's just get going. We'll put in the first couple columns. Don't even worry about what they are at this point. It's just going to be, the first column is going to be the number of the data point, and then the one on the right is going to be a time column that you'll see once we get to the experiment. So up on top, you see A, B, C, D, and on the left, 1, 2, 3, 4, right? Excel puts those things in for you. And so I want you to click in cell A1, right, at the top left here, and just put in like number. Just write in the word number, N-U-M-B-E-R. I'm writing this way too small. Just write in number. And then you can hit tab. Tab will send you over to to the neighboring cell, over to B1. And there you can put in time there, and I always include the units in your tables, because you will not remember what units you use when you go to do your lab. So put time in, and then in brackets after it put seconds. Okay, and then after you do that, you can hit enter. Okay, enter should send you over to cell A2. Right. Enter says take me to the next cell and start at or take me to the next row and start at the beginning. Okay, so then this is where we're going to put the first data values in there. So in cell A2, then you can put 0, hit enter. That'll send you to cell A3, and you can put 1 in there. Okay. All right, now I want you to click. So everybody got 0 and 1. Okay. Everybody's going to have to nod either yes or no, because otherwise, okay, good. All right. So I want you to click on A2 and drag down to A3 so that you select both these two cells there together. Okay. Got them both selected? A2 and A3? Okay, just so you know, if you're not following along, you got to say something, because otherwise I'm going to have to walk you through this later and it's going to be embarrassing. Okay. All right, then bring your cursor over here in this spot down here on the right, and you should see that it changes to a little plus. You guys see that plus pop up there? Okay, so once that plus pops up, click and drag this thing down. Okay, what the plus does is it continues a pattern. Okay, so this should fill in 2, 3, 4, etc. down to put like 30, 32, maybe 33, probably 33 is a good number in there. Okay, so everybody was able to continue that pattern? Yeah? Okay, so you need to select 2 and continue the pattern, right? If you were to just have 1 cell in there, then it would just have like, it would just put 1 in every thing, because that would be the pattern, the only pattern it picks up. Okay, so that's good. Everybody's good with that column? Okay, now you can go and click on B2, on cell B2, and we're going to define here column B in terms of values in column A. So whenever you want a formula in an Excel column, the first thing you hit is equals. So type equals. And then you can click on any cell that you want, and it'll stick the value of that cell right there in the formula for you. So after you hit equals, why don't you go and click on A2, and an A2 should pop up in there. Okay, and then you can do divide by 60 and hit enter. Okay, everybody's good? All right. So then B2 is defined in terms of A2 divided by 60. Now, if you go to this, the corner here until that plus pops up again, okay, go until that plus pops up and then double click. All right, you guys got that? So everybody's got 2 columns. So what the double click does is just, it'll apply that whole thing all the way down. So are there any problems with, so once in a while Excel will be really dumb, and if you have like a number and divide by another number, it thinks you want a day and a month. It thinks you want like the 0th day of the 60th month or something, or the 60th day of the 0th month. Excel is not very smart. Okay, looks like you guys got it all. Okay, good. So it looks like everybody's got this. So, so the plus thing that continues the pattern. If you want to put a formula in, even if you wanted to put like, you know, pi times 3 or something like that. You have to have an equal sign at the beginning. Here, you can click to enter the one cell's value into another one in terms of the definition. You can also just write A2. That's fine. And there's a few more things that, well, I want to show you how to select columns and how to put in a plot. So we're just going to make a meaningless plot right now, and then it'll at least show you where to go to put in a plot, and then I want you to delete the plot. Okay. So if you click up here on the A, right, click on that, it should select all of column A. Okay, hit and hold Control, and then you can click on B, and it'll select all of column B. So now you have 2 columns selected. Then we're going to plot the 2 of them. So go to the Insert column, the Insert menu bar up ahead, up on the top. Over by Charts, kind of somewhere near the middle, on the bottom, you'll see a scatter plot. So that's the one that's just got a bunch of dots, no lines between the dots. If you click on that, something will drop down, and then you can click on that first one that, tell it, no, I really want just dots, no lines between the dots. The only lines you'll ever include on a plot in this class are going to be fit lines. So no need to put arbitrary lines between points. Okay? So when you did that, did a plot pop up? Fairly uninteresting plot. Okay. But now you guys know how to make a plot. Sound good? Okay. Cool. So you can delete that plot then. So that just kind of shows you some of the basic things. And we also set up our first two columns, so that'll be useful. Okay, now let's see. I should be getting pretty close to the point where I can actually talk about physics, which would be great. Yeah. All right. Great. Okay, we can talk about physics now. So let's do that. So we've been talking about kinematics. Kinematics is the study of how things change their position over time. And we talked about free fall. In lecture, and about how objects in free fall have this constant rate of acceleration, which is little g. Right, and the equation for, so there are these kinematic equations for constant acceleration, or KECA, that are really helpful when you have a system that's undergoing constant acceleration. And they look something like velocity final squared equals velocity initial squared plus 2a times, say, change in y. Velocity final equals velocity initial plus acceleration times elapsed time. And final position, say, equals initial position plus v initial times time plus 1/2 times acceleration times change in time squared. Right? Those are the kinematic equations at constant acceleration that you can only use in the event of, in the case of constant acceleration. So if acceleration is changing in time, as it sometimes will in a calculus-based physics course, then you can't use these. Okay, these are only fair game when acceleration is constant. Okay? Okay, so, and so today we're going to do a lab where we measure the position of something that's falling at a bunch of different times, and we'll use that to get the free fall acceleration. Okay, the one equation that we're not going to use is this one. Okay, but we're going to use these in the case of a falling body. So I can replace A with G, the free fall acceleration. Okay? And let's just talk about the free fall acceleration a little bit before we move on. So the free fall acceleration is little g, which is 9.8 meters per second squared. Okay. No, don't use 10. People always ask me if they can round it to 10. No, your online homework system will mark things wrong if you do that. So use 9.8. So the idea here, the free fall acceleration, is pretty simple. That when there are two objects, say, dropped at the same time, they will reach the floor at the same time. I don't think it's going to pick this up. Okay. Let's try it from right here. So if I have these two objects here, I drop them from the same height, they will reach the table at the same time because they both accelerate at the same rate. And this is happening at the same rate for both of these, despite the fact that this one is way heavier than this one. And this one is also made out of different stuff than this one. Okay, so the free fall acceleration is the same, independent of mass or chemical composition. And this is probably not something that's totally mind-blowing to you guys, but it really was something very, very mind-blowing when Galileo first came up with this idea. I think it's helpful to understand why that is, just because it's many of the ways that we think about the world are just so, they're absorbed rather than learned, and they're just really natural to us, and so it's really hard to think about how anybody could think about the world differently. But prior to, say, Galileo and Newton and the discovery of Newtonian mechanics, the reigning paradigm in physics would have been from Aristotle's physics. So in Aristotelian physics, the tape, when I let go of it, is falling down to the ground, not because it's obeying some kind of impersonal mechanistic law, but because that's where the tape belongs somewhere. When I lift it up like this, I'm putting it in an unnatural state. And when I let go, it's fulfilling its purpose. It's achieving its destiny, essentially. It's called teleology. It's the idea that there's some kind of purposive action that's being fulfilled here. And according to Aristotle's understanding of matter, matter is composed of just 4 elements: earth, air, water, and fire. This comes not just from Aristotle, but from the long tradition of Greek thinkers before him. So, according to Aristotle, everything is made up of earth, air, water, fire in some kind of combination. And if you have 2 objects, say, made up of different relative amounts of these different elements, then they probably should fall at different rates. And the reason is that these different elements belong in different places. Earth belongs down below. Fire belongs up above. Right? Think about it. When you light a fire, the flame rises up, right? And during the day, you can go outside and look up, and the sun's up there. At night, you can see the moon and the stars up there. Fiery things appear up above us, right? Whereas things that we drop, they must be made of earth, because there's all of this earth underneath us. So, according to Aristotle, then, if you drop 2 things from the same height, they shouldn't necessarily fall and hit the ground at the same time, because they might be made out of different stuff. So let's see. Aristotle probably would have performed his experiment something like this. Okay. Did those 2 things fall at the same rate? No, right? Not at all, and it must be because this thing has a relatively larger amount of fire composing it, as opposed to this one, which has a larger relative amount of earth, right? So Aristotle has confirmed Newtonian mechanics is wrong, or maybe there's another explanation. So of course, the actual explanation of this is that there's more than one force involved here. So there's the force of gravity pulling down. There's also the force of air resistance pushing up as the thing falls, right? And air resistance depends on the properties, things like surface area and how much of the surface is going to catch on the air as it's falling. So it's a very different way of thinking about the world than Aristotelian physics. But like I said, I think you can't really appreciate how Newtonian mechanics, how it presents this actual huge framework of understanding nature, and it's very much deeply embedded in the way that we think about the world today. And it's actually not entirely true, because there's the realm of quantum mechanics and the realm of general relativity, which is not at all intuitive to us or part of the way that we think about the world, is more correct or holds in more circumstances than just Newtonian mechanics does. So anyway, this was pretty scandalous then when this was first stated, that g is 9.8 meters per second squared and that it's the same for everything. And you kind of need to use your imagination in order to come to that conclusion, because you need to think about, well, how would this look if there was no air? If I pumped all of the air out of this room and this was a perfect vacuum, then this would hold for all objects, right? And there's a famous video from one of the Apollo astronauts who is on the moon, and he holds up a hammer and a feather in one hand, and he drops them, lets them go, and they both fall at the same rate, right? So in the absence of air resistance, all things will fall at the same rate, regardless of what they're made out of and regardless of their mass. Okay, so there's a couple other things that you should know about g, just that it is relatively independent of elevation and where you are on the Earth. So it'll vary a little bit from one place to another. So say you're standing at sea level on top of like a mountain of titanium, g will be a little bit larger than, say, another person who's standing at sea level above a large reservoir of oil, where oil has an average density that's the density of oil is less than the average density of the Earth. So there's less there to pull on you. There's less mass underneath your feet to pull on you. So g will be a little bit less. That's actually one of the ways that you can discover large reservoirs of oil. So g is, but g is, it doesn't vary too much from this across the surface of the Earth. And it will change with elevation a little bit, but that's negligible for most cases. It's definitely negligible for what we're going to do in this chapter of the textbook. Once we get to chapter 6 of the textbook, then we'll get into Newton's law of universal gravitation, and we'll talk about, instead of little g here, big G, which characterizes gravity on the scales of planets and stuff like that. And then you can see that g, the free fall acceleration, is going to be a lot less than this if you're, say, on the International Space Station dropping something towards the Earth. Yeah, g is relatively independent of elevation for most places on the Earth. Okay, so that's a bit about g. Now we're going to perform an experiment where we're going to measure g. Okay, and we're going to use this instrument over here, which is called the Bare Free Fall Apparatus. And this is something that Galileo would have killed to have one of these. So it's a pretty simple thing. Up here at the top, there's an electromagnet. And down here, there's a strip of wax paper, and there's a little wire on either side of this strip of wax paper. I'm going to just get a new strip of paper. Yeah. So, all right, new sheet of paper loaded. Now, I can take this little thing here, which has metal in it. If I turn up the electromagnet, then I can stick that right up there and it'll stay here. Okay. Stop it from wiggling. Now, when I turn the electromagnet off, then this thing's going to fall. And I turn on this thing here and press this button. There's a spark. This is a spark generator. So there's a spark that's generated here at a frequency of 60 hertz. So what that means is that every 60th of a second, a spark jumps from this wire here up in the front, and it jumps between the wire here up in the front and this other wire that you can't see that's behind the strip of wax paper. Okay, so every 60th of a second, a dot will be created, because as the spark jumps across this wax paper, it melts a little hole in the wax paper. Okay, so I'm going to let this thing fall. As it's falling, this spark is going to jump back and forth across the wax paper, and it'll leave for us a little dot at the location where this thing was every 60th of a second as it was falling. Okay? So here, let's do that. So spark generator's going, electromagnet fell. Right? Here's another thing that should have been in the safety talk. Don't touch that. Okay, so as the thing fell, then you could see that it left a dot it left a whole bunch of dots as it was falling. So up here at the top, the dots are pretty close together. Down here at the bottom, the dots get a lot more spaced out. Right? And that's, of course, because the thing started out with very little velocity. It accelerates as it's falling down. So in the same time span, it'll cover more distance as it accelerates on its way down. Okay? So what you have on your tables there is, well, I prepared a whole bunch of these in advance, and they're taped onto the table for you. So let's just write up here on the screen, or I'm sorry, on the chalkboard, the formula for the average velocity. Right? It's change in position over change in time. Right? We've used this a bunch of times by now. Now, that would be, x final minus x initial over t final minus t initial. Okay, so as this thing is falling, you have a record of exactly where it was, its location, at a whole bunch of different timestamps. So you have positions, so you have times, and then you can measure, you can take a 2-meter stick and measure the location of each one of these dots. And then you'll have positions for each one at each one of these timestamps. And you can use that to get velocity as the thing is falling. And from that change in velocity over time, you can get an acceleration. Does that make sense? Okay. Cool. So let's, in a minute, I'm going to have you guys go grab a meter stick. Here, I'll have you, so I'm going to have you guys grab a meter stick, but you have to put gloves on. And then once you're done with the meter sticks, you can just set them back and then throw out the gloves. Okay? I'll have the first grab first. So yeah, just take 2 gloves and go grab a meter stick. And so some other noteworthy things to say. You guys probably heard me say in lecture that the most common mistake that I see in, or one of the most common mistakes that I see in intro physics courses is the failure to consistently apply your reference frame, the coordinate system, to all of the quantities consistently. So let's just talk a bit about reference frames. So you go ahead and grab one. So, okay, you have a strip of this wax paper strip with the dots on it sitting there on your tables. What you're going to do when you make these measurements is you're going to measure the position of each one of these dots, and the orientation of your meter stick, the placement of your meter stick is going to determine your coordinate system, okay? So what that means is if I take my meter stick and I orient it, say, I take my 2 meter stick and I orient it this way, where the numbers are getting larger up here at the top, then I've effectively set up a coordinate system where my y-axis is positive pointing up, right? Positive y points up. And then g will be negative, right? Or, sorry, the acceleration vector will be minus g, right? It'll be pointing down. Whereas if I take this thing and flip it around the other way, and the small numbers are at the top, the bigger numbers are down at the bottom, then the opposite is the case, right? So it doesn't matter which way you do it, but you got to apply it consistently as you're making your measurements to these dots, okay? So you're going to take this thing, and you can see over here on the left side of the table is where the dots are closer together, so that's where it started. You can measure this as, you can measure the dots, so do measure the location of each one of the dots. Don't measure the separation between neighboring dots. Okay, that would actually compound uncertainties as you go and make your measurements. So what you want to do is, so since you want a coordinate system that's consistent, you want to find a good place for this meter stick to start from, and you want to leave it there. Okay, don't go wiggling it around. So I'm going to fix so the ends of the meter sticks are sometimes a little bit ugly. They've been dropped, smacked against the end, stuff like that. So instead of starting out at 0, I'm going to start and put the 10 centimeter mark, you can pick whichever one you want, the 10 centimeter mark right up at the top dot there. And I will make sure that wherever I make my measurements from here on out, that I always make sure that the 10 centimeter mark is located right there at the top dot. Okay, so I would measure to the second decimal place in centimeters. So that's, so the millimeters, the tiniest marks on here would be the first decimal place. So you're going to actually not just go, okay, it's 7 little tiny tick marks down to that first dot, but you're going to say, is it like 6.8 little tiny tick marks away, or is it 7? So you're going to go to the second decimal place. Okay. So, so go to the second decimal place in centimeters, and then you're going to enter these things into this other column up here on your spreadsheet. So you can put on your spreadsheet, say you call this y, in centimeters. I don't really care which units you use. It's just you have to do whatever you do, you have to do consistently. And so I would say, well, this one was 10 centimeters because that was my reference point. The next one was at 10.42. Sorry, you don't want to put letters in here, just numbers. And the next one after that was at, say, 10.79. I don't know if these are realistic or not, something like that. Okay, but you're going to actually put 2 decimal places in there, and you're going to enter these right into the spreadsheet. Okay, and then from this, you're kind of off to the races. You can measure the velocity. You can calculate the velocity from these positions, these times. Right? Again, doesn't matter where your 0 point is. Doesn't matter where your origin is. The velocity doesn't care where your origin is. Right? So